Okay, so let's talk about the triangle removal lemma. Um, so this is just a lemma. It's a well-known lemma that's related to regularity lemma. In fact, we're going to use the Semreti regularity lemma to prove it. And it's just a common application of the regularity lemma. And well, I'm also going to use the triangle removal lemma to prove something else. Anyway. It's a bit difficult to explain the triangle removal lemma in a way that's intuitive. But there's another way in which it's almost too intuitive. So maybe I'll just read the technical statement first. For all alpha and for all positive alpha, there exists a positive beta such that for sufficiently large n, whenever you have a graph on n vertices, such that G minus y has a triangle for every set of edges y up to this size. So in some sense, it's hard to kill all the triangles in G by removing edges. You have to remove, if you're going to remove edges until there's no triangles, the number of edges you have to remove is more than this amount. And if that's the case, then the number of triangles in the original graph G is at least beta n cubed. So, right, the intuitive way of explaining this, it sounds almost too obvious, is just saying that if G is far away from being triangle free, meaning you have to remove a lot of stuff in order to get rid of the triangles, then that must mean there was a lot of triangles. In some sense, that's what this is saying. Of course, it's more specific than that. We have something going on with these powers of n. Like here I have n squared and here I have n cubed. Roughly speaking, that sort of makes sense because y is a set of edges, and how many edges do graphs have? In general, a graph could have up to n choose 2 edges, which is a quadratic. N choose 2 is roughly 1/2 n squared, so it's a quadratic number of edges. So it makes sense to talk about sets of edges that are quadratic in size. Meanwhile, how many triangles do graphs have? In general, a graph could have up to n choose 3 triangles. N choose 3 is it's n times n minus 1 times n minus 2 over 6. That's as n grows, that's cubic, right? It's basically 1/6 n cubed. So it makes sense to talk about sets of triangles being of a cubic size. So yeah, maybe I'll leave my explanation of the statement of the lemma at that. It's still a little bit not exactly intuitive in my opinion, but I'll leave the discussion at that and let's just prove it. So, like I said, the proof is going to follow from Semreti's regularity lemma. We're going to apply the lemma to this graph for some epsilon that we'll talk about later. And of course, so here's the statement of Semreti's regularity lemma. This is just a page of notes from last time. And when I say apply the lemma to G, basically I mean get this partition. Because what the lemma says is that for whatever epsilon we choose, and we'll talk about that later, there exists an M such that for sufficiently large n, and we do have sufficiently large n, we're assuming that our graph is sufficiently large, we can get this partition into these parts with these properties. And yeah, maybe it would be a good time to pause the video and remind yourself what these properties are and what these mean. But I'll just go ahead. So that's what we mean when we apply the Semreti regularity lemma. We get this partition. Now, what we're going to do is we're going to delete some edges based on the partition that we see that Semeretti's regularity lemma sort of spits out for us. First of all, so we have this partition into parts V naught. It's like V naught, V1, all the way up through VT. And some of those pairs, VI, VJ, are epsilon regular, and some of them aren't. I'm going to delete all the edges between pairs that aren't epsilon regular. Then I'm going to delete all of the edges that have both ends in the same part. So I'm going to delete the edges within V0, V1, V2, and so on. Then I'm going to delete edges between pairs of low density. So any pair that has density less than delta, where delta is some number that I'm going to choose later, I'm going to delete the edges between such pairs. Then I'm going to delete any edge touching V naught. If you remember, V naught was this funny set, we call it the rubbish bin, that there's basically no requirements for V naught except that it be small. So I'm going to delete all of those edges. And, well, how many edges did I just delete? Okay, so in step 1, it was edges between non-epsilon regular pairs. Well, the regularity lemma says that the number of pairs that are not epsilon regular is at most epsilon t squared. So here's the number of pairs we could possibly have, and then how many edges could I possibly have between such a pair? Well, so suppose I've drawn this here, and this is VI, and this is VJ. VI is at most n over t, right? Because, so sorry to keep going back and forth, but I'm going to do this a lot. In the statement of the lemma, V naught is less than epsilon n, but the rest of these are all the same size, right? Even if V naught was empty, these would all be n over t. If V naught was this size, then it would be like n minus epsilon n over t. But in any case, these VI and VJ, they're at most n over t. So once again, how many edges could I possibly have? Well, n over t times n over t. So that's what I did here. This is the number of pairs that could possibly be non-epsilon regular. This is the number of possible edges you could have between any two such pairs, and I simplify that and I get epsilon n squared. Okay, what about step 2? We deleted edges within parts. Well, there's t parts. Okay. There's t plus 1 parts, but I'm not going to talk about V naught later. We delete all the edges touching V naught in the last step. So for step 2, maybe I'll just say this is a little bit picky and technical, but let's say we're just deleting the parts within V1, V2, and so on, not V0. Anyway, that's silly. There's t such parts, and you know how many edges could be within a part. Well, each part has size at most n over t, so you do that, choose 2, and then simplify this. And so anything choose 2 is at most 1/2 of that squared, so I'm just going to use that here. Simplify it, I get this, and then recall that, here I go back to this page, recall that t is greater than or equal to 1 over epsilon. So when I get to here, I can replace this t with a 1 over epsilon, and the inequality goes the right direction for me to do this, and get epsilon over 2n squared. Like that. Okay, let's keep going. Step 3, we deleted edges between pairs of low density. Um, and right, so how do we bound the number of edges we just deleted there? Well, even if all of these pairs, t choose 2, even if they all had low density, so I'll just do the number of pairs times this is the number of edges that could be going in between a pair that has low density, right? Because the density is the proportion of edges that are present, right? So n over t squared is the number of edges that could possibly be there if there was every edge there. But if we're saying that this is a pair of low density, then only delta fraction of those are actually going to be there. So I take the total number that there could be times the density. And if I take that and simplify it, again, I'm just going to use t choose 2 is less than or equal to 1/2 t squared, and then a t squared cancels, right? So I get 1/2 delta n squared. Finally, for 4, I'm going to do something really silly. How many edges could possibly touch V0? Well, pick a vertex in V0 and then pick any other vertex in the entire graph. I mean, I could write n minus 1 here, but I'm really being sloppy with my bounds. You know, when we do this, n is so large that subtracting 1 doesn't even really help. We don't worry about such things. In any case, we get epsilon n squared as a bound for that. Okay, so in total, what do we got here? Epsilon n squared, epsilon over 2n squared, another epsilon n squared. That would make 5/2 epsilon n squared. And then we also had this 1/2 delta n squared. So I collect like terms and I get this. Okay, let's take a step back. What just happened? I have described a set of edges that I want to remove, and I have shown that that set of edges is not very large, and it's no larger than this. And what we're in the middle of is a proof where we're talking about a graph such that the removal of any set of edges y up to a certain size can't possibly remove all the triangles. So here's what we're going to do. I'm going to choose epsilon and delta because I haven't really talked much about the choice of epsilon and delta. These proofs are it's really more enlightening and it's more instructive for where maybe you could have the hope of writing a similar proof in the future. It's a lot better if we run through the proof and choose epsilon and delta basically at the end. We'll just run through the proof, we'll see what epsilon and delta need to satisfy in order for it to work, and then see whether we can choose epsilon and delta to satisfy that. That's really how the thought process goes when you're coming up with such a thing. So we would like to say that after removing all these edges, we still have a triangle. So I'm just going to choose epsilon and delta so that this number is smaller than alpha. In other words, the number of edges that we removed is smaller than alpha n squared. So we'll just remember that. We'll remember that in the end we need to make sure that whatever epsilon and delta are, this number needs to be smaller than alpha. And then we would still have a triangle. So how could we possibly have a triangle in that graph after removing all of the edges that we removed? Well, it would have to be a triangle with 3 vertices in 3 different parts because we removed all of the edges within parts. So, right, it would have to be in 3 different parts. they couldn't be V naught because we removed all the edges touching V naught at all. So we have some VI, VJ, VK, and IJ and K are not zero. All of these pairs would have to be epsilon regular, because if they weren't, then we would have removed that edge. And all of these pairs have to have density at least delta, because if they didn't, then we would have removed that edge. So the triangle basically has to look like this. It's a triangle between three pairs that are all sort of good pairs. They're epsilon regular, and they don't have terribly small density. And their sizes, if you recall, Semmeradi's regularity lemma spits out a partition where these three would be equal. Well, they aren't V naught, so they aren't the exceptional set, so that all the sizes are equal. And let me just write a lower bound on their size, because once again, there's n vertices total. Epsilon n might be in V naught. Maybe I'll pull up this picture again. Yeah. Epsilon n might be here, and then the rest are all equal size, and there's t of them, so you would just take n minus epsilon n and divide by t, and t is less than or equal to this number m. So that's why instead of dividing by t, I divided by m, because I wanted the inequality to go the right way. So all I'm getting at here is that these have linear size. Linear because I see some constant times n. All right. Now what we're going to do is count the triangles, because in the end, the conclusion we have to reach is that the original graph had at least some cubic number of triangles. So here we go. Recall something that we proved about epsilon regular pairs. For example, if VI and VJ are epsilon regular, then at most epsilon proportion of these vertices have a degree into this set that's significantly less than what it should be. More specifically, more precisely, in VI, there's at most epsilon times the size of VI vertices, whose degree into VJ, the number of neighbors in VJ, is at most density minus epsilon times VJ. And I'm just going to basically cut those out. Similarly, the vertices in VI that don't have that have an abnormally low degree into VK, that there's not too many of those either. That's why I wrote respectively VK here. So other than these two small subsets of VI, if I choose a different vertex in VI, it has degree at least delta minus epsilon VJ into here, and it also has degree at least the same thing into here. So let V be in any other such vertex. So V is just in VI, and it has large enough degree here and large enough degree here. I'm going to let A be this neighborhood, and B be this neighborhood. Well, more precisely, A is the neighborhood in VJ, and B is the neighborhood in VK. And A and B are not too small because we chose V so that its degree would be large enough. So A and B are at least delta minus epsilon times this. Now, what I'm going to use is I'm going to use the fact that Vj and Vk is epsilon regular, right? What I'm trying to do is I'm trying to count triangles. So I see it, for every edge from A to B, that's going to be a triangle, right? And there are a lot of those because Vj, Vk is an epsilon regular pair, and if this is an epsilon regular pair, then I can take a subset of this and a subset of this and talk about the density of edges between those two subsets. More precisely, and this is another spot where we have to talk about our choice of epsilon and delta. Right. Vj and Vk, that this is an epsilon regular pair, and I have a subset A and a subset B, but I have to make sure that these subsets are large enough, right? Because, right. For an epsilon regular pair, this is just the first page of the notes from last time. For an epsilon regular pair, you have to be talking about subsets that are large enough, right? Like A prime's a subset of A, B prime's a subset of B, and A prime has to be at least epsilon times the size of A, and B prime has to be at least epsilon times the size of B, and then you can talk about the density. If A prime is too small or B prime is too small, then all bets are off regarding the density. So we need to talk about that, at least, for a second. But right, so basically A just needs to be at least epsilon proportion of Vj. We know that A is at least this. So if I choose delta to be at least 2 epsilon, then this is at least epsilon. So A would be at least epsilon times the set that it lives in. And also B would be at least epsilon times the set that it lives in. So I'll just make a note of that. That goes on our list of requirements for epsilon and delta. And as long as that's the case, we can talk about the density between A and B. So once again, the number of edges between A and B would be, I take the total number of possible edges, which would be size of A times the size of B, times the density. And the density would be at least this, because the density, the density from Vj to Vk is at least delta, and the density from A to B is going to be within epsilon of that. So the density between A and B would have to be at least delta minus epsilon. So the number of edges, once again, from A to B would be at least this. And then I plug in a couple of things because A is at least this and B is at least this. So I plug those in and I get this. That's the number of edges from A to B, or a lower bound on the number. And each one of those forms a triangle with V, right? But now, remember, okay, let me take a step back here. We're not done yet because we're counting triangles, but I want a cubic number. And so far, I just got a quadratic number. But now, basically, I just have to say that I have a lot of choices for V. This was all just for a single fixed V here. The number of choices that I have for V is at least this, because remember, V was just an arbitrary vertex that it didn't have a low degree into Vj and it didn't have a low degree into Vk. So we cut out this bad set of vertices and this bad set of vertices, and the good vertices in Vi is at least 1 minus 2 epsilon proportion of them. And so that's at least this, because this is just going back to we have this information about the size of Vi, Vj, Vk. So the number of choices for V is at least this. And for each choice of V, we have at least this many triangles, and we multiply those together and get this. So we have some god-awful constant. That's the constant that we're going to call beta, right? Because we are just proving, we're proving the existence of a beta such that you have at least beta n cubed triangles. So that would be your beta. And then, yeah, maybe I won't say too much in detail, but just to wrap this up, because I promised I would say something. It's clear enough. Geez, where did I go? Yeah. Really, about this list of requirements for epsilon and delta, all we needed was to choose epsilon and delta such that this was smaller than alpha, and also that delta is greater than or equal to 2 epsilon. So, yeah, I don't know. Probably, let me be really safe here and say that epsilon can be alpha over 100, and delta can be 3 alpha over 100. Sure enough, delta is greater than 2 epsilon, and 100 is a big number, so presumably this is, if we plug this in, this will be less than alpha. So in the end, that wasn't hard to choose the epsilon and the delta. All right. So yeah, before I stop recording, let me just preview where I'm going with this. Well, part of it was just to get comfortable using the Semeretti regularity lemma, because the truth is I really want the regularity lemma because we're talking about extremal graph theory, and I want to prove Erdős-Stone-Simonovitz theorem. But the proof of that theorem is maybe a bit harder than the initial proofs using regularity lemma, like the one we just did. You might not think the one we just did was that easy, but there are similarities between that proof and the proof of Erdős-Stone-Simonovitz, and so it's a decent warm up. Anyway, there's also the fact that historically, the Semeretti regularity lemma, and the reason why it's called a lemma is because, of course, it was used to prove something else. It was used to prove something about arithmetic progressions. And yeah, so maybe now I'll just tell you what Roth's theorem says. For all epsilon greater than 0, and for all sufficiently large n, whenever you take a subset of the integers from 1 to n that has density epsilon, we may have noticed we're using the word density a lot lately. When I say density epsilon, of course, I just mean that we chose a at least epsilon fraction of them. The proportion of the proportion of elements that are in A is at least epsilon. Then any such set has a 3-term arithmetic progression. So A has to contain a subset of 3 elements, A plus D, and A plus 2D. And of course, D can't be 0 because that would be cheating. That would be too easy. So, right, that is Roth's theorem. And Semeretti's regularity lemma was originally used to prove a generalization of this that is called Semeretti's theorem. Um, Semiretti's theorem basically is if you just replace the number 3 with the number k, and a k-term arithmetic progression, of course, you would just go a plus d, a plus 2d, a plus 3d, a plus 4d, until you have k things. So a k-term arithmetic progression is basically just a set of k elements that are all evenly spaced out. The difference between two consecutive terms in the sequence is always the same. And so this theorem is true for any k, and that's Semiretti's theorem, and that was the original use of Semiretti's regularity lemma. So there's a lot of history here. Of course, this one's called Roth's theorem because Roth actually proved this for k equals 3 before Semiretti proved it for general k. But what we're going to do next time is I'm going to prove Roth's theorem using the triangle removal lemma, which of course is not the original proof. So yeah, that's what we'll do next time.